Welcome back, ladies and gentlemen. Here we're talking about forces and an introduction to forces in Newton's first law of motion. And we'll get to Newton's laws throughout this unit. Really cool stuff. But forces first. Real basic definition of what a force is. It's simply a push or a pull on an object. That's really it. But there's, of course, details that we have to pay attention to. So you'd agree that how hard you push or pull on something matters, and which way you push or pull on it will also matter. Therefore, forces are vector quantities, so they have both magnitude and direction. So these guys are vectors. Now that's going to mean that forces can be combined just like any other vector. And we'll be looking at some of that. We'll have to use those skills. Now, types of forces. Well, there's some general categories. For example, you could have weight of an object. And commonly, capital W with an arrow over like that. The arrow on top indicates that it's a vector. And the capital W, in this case, is weight. Now, some sources, instead of that, may give you the force due to gravity, like that. Fg is force due to gravity. Okay, that's fine. There might be a force you apply. So you just call it applied force. It's like, you literally pushing on something. It's an applied force. And so generally that's just given the F symbol with the arrow overhead. And now one way that a force can be applied is if you put tension on something, like you tie a string to it and you pull on the string, or something else pulls on the string. So that's a capital T with the arrow over it. There's another force that's going to be really important for us, and it's called the normal force. And the word normal, you've heard that before, and capital N with the arrow over it. Sometimes this is force normal like that. Oh, by the way, the tension. Sometimes the tension is force of tension, like that. But the normal force. Okay, normal means perpendicular. So this is a support force from a surface. An object like sitting on a surface or touching a surface, and the surface provides a normal force to that object. It's a very important one. Also, we could talk about friction, which is always all around us. It's unavoidable. Force of friction. There are two kinds. I'm not going to get into the two kinds of friction right now, except for the symbols. The force of friction is going to be F sub S or F sub K. Don't worry about the differences right now, but if you see those, that's telling you friction. There are probably many other kinds of forces and many other types. I'm not going to worry about those right now. Instead, let's look at what do we have to do in order to represent forces, especially on a diagram. And this is something that AP absolutely requires. This is a skill they demand, and they will absolutely ask you to do this on the test. How to draw a diagram of forces acting on an object. So what I want to do is I want to just kind of see if I can get my artistic skills going a little bit. And you're going to see this thing take shape a little bit. Okay, so maybe this sort of looks like a stroller. Oh my goodness, right? So we have to ask ourselves, well, what are the forces acting on this thing? What we're going to do is first, this is not the kind of diagram that the AP exam will want. We're gonna do a few things on this, and then we're gonna create the actual diagram. Well, this thing has weight. Gravity will be pulling us down. Oh, by the way, we're not done studying gravity either. But let's identify some forces here first. All right. So there is gravity, weight. I need an arrow because it's a vector, and the length of the arrow matters because that shows magnitude. The direction of the arrow shows the direction of the force. So there's weight. And I have a normal force. Remember, this is a surface, and it's going to be applying a force to the object that is perpendicular to the surface. So here's my normal force with the arrow above it. And I know technically it's supporting in 2 places, so you could draw it twice and you'd have to do a bunch of weird stuff. I'm not worrying about those details at this moment. But how about the diagram that AP will ask you for? The diagram they're going to want is called a free body diagram. You have to be able to do these. So, what does it entail? Well, what we do is we have first identified the forces acting on this object, and the best way to do this that I've learned is ask yourself, well, are there any contact forces at play here? Because if you think of this list, right, you can look at this as being anything on this list, anything you could put on this list could either be a contact force, where something's actually touching it, or what's called a field force. Contact or field. Right? Now, weight. Does the Earth have to touch an object to give that object weight? No, it doesn't. And so this one absolutely is a field force. And that's what we mean. There's a gravitational field that is affecting objects. What about applied force? What if you push on something? Well, that's contact. Tension. Tension is interesting. You pull on a string, the string pulls on the object. Well, it's touching it, so that's contact. Normal support force, contact force. Friction, well, there's got to be contact for friction to happen. And interesting thing with drag, with air resistance, it actually is friction because you're in contact with those air molecules. So we're going to ask ourselves contact and field, and that helps break this down for us when we're trying to identify these forces. What's touching the stroller? The ground. There's a normal force because that's a surface. And that's it. Nothing else is touching it. Are there any field forces? Are there any gravitational fields? Well, yes, there is. There's the gravitational field of the Earth, so there's weight pulling down. There are other examples of field forces. For example, there could be a magnetic field, or you could take into account the gravitational fields of multiple objects, but those calculations get pretty involved. So that's what we have to do. We have to identify the forces. We've done that. But then for this thing called the free body diagram, what we do is we separate away everything but the object that the forces act on. And we represent that just with a dot. Just draw a little dot. That's it. Then you draw the forces acting on the dot, because you're drawing the forces acting on this object, not forces caused by this object, only those acting on it. And so we have these two. But what I want to do is I want to draw these arrows for these vectors, starting at the dot and going away from it. So I have an arrow going down, and that is the weight. And I'll label it. And I have an arrow going up, and that is the normal force. And there's a reason I'm trying to make those two the same length. You probably can tell what that reason is. Okay, now I also will want a coordinate system. And this is, sometimes you think of it as a formality, but it can matter. So positive x, positive y. And I have my free body diagram, and that's it. Pretty easy when you think about it, but so important that you be clear, right? The direction of these two arrows absolutely matters, and the lengths of those arrows absolutely matters, because those lengths imply something that we get to in a little while in this chapter, in this unit. Now, what if though, what if someone comes along, let's say there's a baby in there, and mom comes along and grabs the handle and starts pushing on it, right? So mom applies another force to the stroller. And, well, that's a different situation. So what's that going to look like? We have the stroller. Oh, you know what? I can just, I'll just put it here. This is an applied force right there. Okay. Well, in this case, I would draw a different free body diagram. And the reason is, here's my dot. Now I have three forces acting on this thing, and so let's get those drawn in. So just like before, I have the weight straight down, I have the normal force straight up, weight, normal force, Now I have to add this applied force, and I have to maintain the angle. It absolutely matters. Angle and length as best I can. Force applied. And I will want my coordinate system all over again. This is a different diagram. Y, X. Okay. Now that's it. So separate situations here. And when AP asks you to draw a free body diagram, this is precisely what they want. They do not want any forces broken up into their component vectors in the original free body diagram. What they want you to do is they want you to break up break up the vectors into components separately. And so you might do something like this. In fact, you should do something like this, but then separately off to the side, you can, let me go to a different color here. I'll try blue. Off to the side, what you can do is you can say, well, I'm going to break up that applied force F. So I duplicate that force F, and I can, this is now F in the Y direction, and I can, this is now F in the X direction, and that is breaking it up into the components. And so you would typically do that separately, away from your main, or not away from necessarily, but separate from your main free body diagram. Absolutely do not do this on this part of the diagram. Please, just so you know. Okay, so that's what happens if you add another force. You just add it to your free body diagram. Awesome. And then, so we have seen some notation for forces. We have seen how to draw forces in this very important type of diagram, free body diagram. Sometimes, often called just FBD. You're going to draw the FBD. Okay. Well, now part 2 of the topics for this video is Newton's first law of motion. Now, when you're talking about Newton's laws, they are laws of motion. And his first law is often called the law of inertia, sometimes, aka law of inertia. You've heard that before, but I don't know if you know what inertia means. So check this out. We have an object. There's my asteroid, my space rock. No, really, it is. I swear. And so we can observe this thing. There it is. There it still is. And it's still there. And so now the thing is, well, I want to get this thing to do something. So I kind of have to apply a force to it to get it to do something. When I stop applying a force, it stops doing something. And this is something that people could observe all the time, forever. And the thing is, they misunderstood this, because they would say, hey, look, that's not going to go anywhere until I push on it. And when I stop pushing on it, it stops moving. And so people used to think for many, many centuries that motion required a force. Turns out that's not true. It turns out that an object at rest will remain at rest just like it's doing there, right? Not going anywhere. There it is. But as long as no net force acts on it. Also, a moving object, so I can get this guy moving. It'll stay moving as long as no net force remains or acts on that. The moving object will maintain that velocity. It will maintain that speed in that direction as long as no net force acts on it. And so what's going on though? You say, oh, wait a minute, what the heck, man? Because if you do that, well, you're applying a force to it. And you stop and there's no force. Well, actually there was. The unseen force of friction between the space rock and the paper are what kept this thing going, really, at this constant velocity. And when I stop, the friction stops that motion. But once I stop pushing, the friction actually goes away, and it's still maintaining its constant velocity. There's a shorthand way to write Newton's first law. It's basically this. If the net force is 0, excuse me, then I'll move my space rock here. Then the object's velocity will remain constant. Now there's a lot implied in this statement. Net force, what the heck does that mean? Well, that's the overall force, the overall effect. And because forces are vectors, they can be added together. When you add them together, you might have everything cancel out, as we did here before we added that. Those two things would cancel each other out. And this stroller would simply remain where it is. Its velocity will remain constant, but constantly 0. It's not going to do anything. Once you have an unbalanced force, the net force is no longer 0. And you can kind of see how it would be unbalanced when you look at this free body diagram. We'll work out the details quantitatively later. Then all of a sudden, the stroller's motion will change. It's going to start to go somewhere. And that's what this is talking about. And so the thing about this is, basically, all objects have mass, but mass is lazy. And that's where this word inertia comes from. Inertia literally means laziness. And, they want to keep doing what they're doing. It wants to do that. It doesn't want to do anything else. Now, if I could eliminate all friction, if that were possible, or let's say if we were in deep, deep space where there was nothing else around and this thing was moving, then what it would do is it would want to keep moving at the same speed and in the same direction that it's going, because there's nothing acting on it that will change that. And so that is Newton's first law of motion. Is that possible? Is it possible to go anywhere where there is no friction or there's no forces acting on something? Well, no, not really. But we can approximate that, and we can play make believe and imagine those situations for sure. Now, there's something else that's very important, although we won't deal with it much, and it's this idea of what's called an inertial reference frame. I'm going to write those words. Inertial reference frame. And what I'd like you to do is read about that in your book. And it's simply the idea that, Newton's laws, including the first law, they really only work in this thing called an inertial reference frame. And basically all that means is your point of view of a situation needs to have an acceleration of 0 in order for Newton's laws to make sense and to actually hold and to be working, to be evident. If, for example, you're in a car and the car's moving at a constant speed going straight down the street, then aside from noise and aside from looking out the windows, and you really can't tell that you're moving. It feels the same, except for some bumps in the road here and there. It actually feels the same, and there really is, believe it or not, there's no test that you could conduct inside a moving reference frame, as long as your acceleration is 0. There's no test you can do that'll tell you that you're moving. That will also not tell you that you're standing still. That's a weird sort of abstract way of thinking of it, but we'll consider this. And so, in real life, this isn't true, but our reference frame here on Earth's surface is so close to this that we do see Newton's laws working, at least on a macro scale, on an object's on a scale of objects that are large enough to hold, large enough to deal with, from tiny pebbles and space rocks up to planets and stars, then the idea of this inertial reference frame works. Okay, that's enough for now. Thanks for watching. I'll catch you next time.